This course section will be about classes and objects, and about keeping your classes and objects clean and working with objects in a clean way. Now, therefore, of course, it won't matter to you if you're never ever working with classes or objects in your code, but if you do work with classes and objects in any way, even if that's not a 100% object-oriented style, then you will get important information out of this course section. Because we are going to have a closer look at classes and objects, and we're going to learn that we can differentiate between real objects, if we want to call them like this, and data structures or data containers, and what that difference is and why it matters. We'll have a look at a bunch of object-oriented principles, which even help you if you're not following a 100% object-oriented style. We're going to have a look at the solid principles there and at the law of Demeter. And we're also going to take another look at polymorphism and see how classes can also help us with that. It is a concept we already had a look at in the last course section. Now we're going to take another look in this section. Now, this course section will still have a couple of demos and examples, but it will be a bit more theory than the last sections, because in this section we'll have a couple of core principles and guidelines which you should be aware of when working with classes. Now, before we dive into the different aspects I want to cover in this section, let me make one thing very clear. This course section will not teach you object-oriented programming. It will not teach you that. This is not the focus of this section and not the focus of this overall course. The idea of this course is to give you general concepts and rules and ideas which you can follow to write clean code, no matter how you write your code. This course is not focused on object-oriented programming, and this section isn't either. We are going to explore various concepts which come from the object-oriented programming world and which apply to classes, but as I mentioned before, this will matter to you if you're working with classes in any way, even if you don't build your entire project in an object-oriented way. Therefore, we're also not going to dive into all possible object-oriented programming patterns and practices. I am going to cover some important core principles which you should be aware of, but this will not be a deep dive object-oriented programming section in general. That's simply not the idea behind the course. The idea is to give you all the core tools you need to write clean code. And for that, of course, we must not forget that clean code is simply code which is written such that it's readable and easy to understand by humans. Now, all these patterns and principles which exist, they help you write code which is maintainable and extensible. Of course, there is a relation to clean code. If you follow these patterns and principles, you tend to end up with clean code, but you could also follow a lot of these principles and still write bad code. That's why we definitely focus on the clean code part here instead of covering all possible patterns and principles. If you are interested in all these patterns and principles, a course focusing on just object-oriented programming is, of course, the course you want to take. So now, with all of that out of the way, let's dive into the first important concept I want to cover in this section. And that's the difference between real objects and data structures. Though I also want to already make it clear that both terms, real objects and data structures, are made-up terms. These are not official terms you will find anywhere, but this is simply a differentiation which you sometimes find out there, which can make sense when you're working with objects. So what is the difference between real objects and data structures, or data containers, as we could also call it? A real object hides its internals, its properties, for example by making them private, and it just exposes a public API, a couple of methods which allow you to do various things with this object. And with these methods, I don't just mean getters and setters for these hidden properties, I mean real abstractions, so methods which do more complex things than just setting a property and therefore acting as a proxy. Data containers or data structures, on the other hand, are simple objects where the properties and internals are made available publicly and where we have almost no public API besides that, almost no methods. Therefore, real objects matter a lot if you're following an object-oriented programming style, and even if you don't, some real objects could be helpful for encapsulating and grouping logic together, and they contain your core business logic therefore. On the other hand, data containers are really just that. These are objects which are just used to store and transport data. For real objects, as I mentioned a couple of seconds ago, we prefer abstractions over concretions, which is a fancy term which simply means that we want to expose methods which define a certain task that should be done, and then we don't care about how the object executes this task. Whereas a data container doesn't really have any methods, and therefore there we just have the concrete data which is stored inside of it, and we can utilize that data in the places where we get access to the data container. So we don't tell the container to do something, as we would do it with a real object, we just can use it however we need to use it. And for example here, we have a database class which could be used to create real objects, because it's hiding its internals, and it then has a public API which abstracts away the internals. Connect and disconnect are pretty high-level methods which then internally do everything to set up a connection or to close a connection. And we don't know what exactly the class will do internally if we just call these methods. That is what abstraction means. We just connect to a database, which is an abstract concept, and how exactly that works is hidden away from us and is not our business if we are using such a database object. On the other hand, this user credentials class here could be used to simply create a user credentials data container. All the data is exposed publicly, we have no methods, and we could just use objects based on this class to pass credentials around, for example as a parameter to a function or a method. And that's the difference between real objects and data containers. We can use classes for both to define these objects, but then how we use them differs. And now, of course, the question is, why does this matter at all? Why should you care? You should care about this differentiation because you can end up writing bad code, not clean code, if you mix these concepts. Let's say you have this database class which has all the logic for connecting and disconnecting. You could be using such a class because you are using an object-oriented approach, or maybe also because you use a procedural programming style, but you still use some classes to hold some of the logic. Whatever you do, here you might have this class, and this class has everything you need to connect and disconnect. So you could use it like this. You could instantiate it, pass in your connection URL, pass in this engine which you got from somewhere else, maybe from a third-party package, and you call connect. And of course you can now also call disconnect. And this would be very clean code. You would be using this object in a clean way, and the place where you write this code, which could be in another method of another object, would also be very easy to read and understand. In addition, whenever the connection or disconnection logic changes, you don't need to make any changes in this part here, you would just make these changes internally in the class. Now, if you mix the idea of such a real object and a data structure, you could, for example, have a public connection property, which means that this connection is now available outside of the class as well. Hence, somewhere else in your application, you could decide that you want to close your database connection, by accessing the database connection and then call close on it, which in the end is what we're doing here inside of disconnect in the class as well. The problem just is the class knows how to deal with this connection because it is its main job. And whenever the logic would change and close would, for example, change from close to disconnect or anything like that, we would only need to make this change inside of this one class. And everywhere where we use it, this change would automatically be applied without changing any code. If we instead dig into our class like this here, and we call close ourselves somewhere else in our code, then whenever this logic changes, we need to change this to disconnect everywhere in the code where we used our database class like this. In addition, even if this never changes, this is harder to read. All of a sudden here in this place where we're just dealing with a database, we now also need to understand how to deal with a connection in addition to dealing with a database. This is more to understand, to keep in mind, and to read. And therefore, this is not good code because of multiple reasons. And that's why this differentiation matters. There are times when you just need a data container. For example, as I mentioned before, when you pass it as a parameter to another method. But then there also are times where you need a real object which hides its logic away, and where you don't dive into the object to then mess around with it. So it is fine to use either of the two concepts depending on what you plan to achieve. But you shouldn't mix them as I'm doing it here by having this public property and by exposing some internals to the outside world. That's why this differentiation matters and why you should keep this in mind when you are working with classes or objects in your applications. So now that we know about the difference between real objects and data containers, let's dive into another important concept, and that would be polymorphism. Now, we already had a first look at polymorphism in the last course section, where we built a factory function which created polymorphic objects to hold different functions for handling payments and refunds. And I explained what polymorphism is back then. It's simply an object or a method which always has the same structure and the same name, but which then does different things based on how it was created and how you use it, therefore. And that's a powerful concept because it can help us avoid code duplication. We can also implement polymorphism or use polymorphism when working with classes instead of creating objects or dictionaries on the fly as I did it back in the last section. So here is another class, the delivery class, which has a private property purchase, a constructor, and then two methods, deliver product and track product. And in there you see something similar as in the last course section. We have different delivery types on this purchase, which is part of the delivery, and based on the different types, we then dispatch different static methods on some other object, some other class here. And this is just some dummy code. Both the purchase and the logistics object doesn't really exist, but I can still show you what polymorphism is at this example and how you deal with it when using classes. Because when using classes, we can implement polymorphism in a very, very elegant way. The solution would be to not just use one class, but to have multiple specialized classes, in this case for the different kinds of delivery we have. Express delivery, insured delivery, and standard delivery. And we would just have a base delivery class, which holds all the shared logic and properties, which all specialized classes need as well. But then it would be the specialized classes which have the specific deliver product and track product implementations. So if we would want to make this class and these methods use polymorphism and be polymorphic, then we would in the end create a couple of new classes. For example, an express delivery class, but also a ensured delivery class and also a standard delivery class. We create these specialized versions because these are, in the end, the three kinds of deliveries we have if we have a look at these methods. We see that the type of delivery seems to play an important role. So since this is the delivery class, which is responsible for delivering a product or for tracking it, we should have specialized versions of these classes for the different types of delivery. So therefore here we would have these three classes. And for example, in the express delivery class here, we would then have a deliver product method. So we can copy this, but it wouldn't have any if check. It would just have the code which needs to be executed to deliver a product with express delivery. So in this case, I would reach out to logistics and then call issue express delivery. Now, the purchase property is not accessible here because at the moment this is a standalone class which doesn't have a purchase property. The solution is to extend the base delivery class here, because when we extend that class, then we also have access to all the properties this class has, including its property. Now, as a quick side note here, of course here I'm using inheritance, and I'm using a couple of concepts we know from classes and the object-oriented world. Later I will also use an interface. If this is all something you never heard about, then you probably never worked with classes, and then of course this specifically is a concept you won't be able to utilize and you won't need in general. You still learned about polymorphism in the last course section though. As I mentioned earlier, the idea of this course and of this section is not to teach you classes or object-oriented programming, but to teach you a couple of concepts and ideas and rules you should be aware of when working with classes or objects. And here we're working with classes, so therefore, of course, this general knowledge about classes, and that includes inheritance, is of course required. You can of course skip this entire lecture for the moment if that is something you don't have any experience with. The only thing here is that this property is private at the moment, which means it can really only be used in here. And if you are using a programming language which knows the concept of private, public, and so on, then you know that you should change this from private to protected. Which means it can still not be accessed from outside of the class, but it can be accessed by child classes, which is exactly what we need here. And with that, we could then also copy over track product like this, and also get rid of the if statement here, and just call the code we need to track a product. And now we repeat this procedure for the other classes as well. So we copy these methods also into ensured delivery, get rid of all the if checks here and just keep the code we want to execute if we do have an ensured delivery, and the same down here for tracking a product. And then again, we copy it also into standard delivery and remove all the if checks and just keep the standard delivery code. Of course, standard delivery and ensured delivery now also need to inherit from the base delivery class, which in the case of TypeScript is done like this. So now we have these specialized classes. In the base class, we can now remove the deliver product and track product methods, because that is something our specialized classes will deal with. Now, of course, you might now ask, that's all great, but where's the if statement? I mean, we need to decide somewhere which specialized class should be used. Well, that's something you need to do in the place where you plan on using these classes. So if you had some code in some other method or function, it doesn't matter where you wanna use such a delivery class, you would in the past have created your delivery class by instantiating a new delivery and passing in some purchase object. And then in the past, before we created these specific versions, you could have called deliver product. Now that's not possible anymore because deliver product doesn't exist on the base class anymore. Instead, you need a specific class now. And that means that in the place where this code should execute, you need to decide which specific version you need. But that's a decision you typically can make in these places. Now you just need to have your if check in that place here. So here you would have your if check with these different branches, and you could also use a switch case statement, of course. And then here you would have your delivery variable, which would be of type delivery. And then here we would assign a value of new express delivery and pass in our purchase. Here we would have a new ensured delivery instance, and down here we would have a new standard delivery instance. And then at the bottom, we can call deliver product. And of course, instead of this purchase delivery type, you would have your purchase object lying somewhere around here where you do execute this if statement. Let's not worry about this condition at the moment though. Let's assume we are in some place where we do have access to this purchase. Because this is pseudocode anyways. It won't execute anyways because we don't have a real purchase here. This is how you would solve these situations though, how you would create the proper instance of your delivery class based on which specific type you need. Now here actually my IDE is complaining that this is not a method of the delivery class, and that would be correct. It's the child classes which added. But of course you can work around something like this as well, for example by utilizing an interface or abstract classes. So here we could have an interface called delivery, which dictates that we have a deliver product method and that we have a track product method. And then this here would be the delivery implementation, for example, and we would extend delivery implementation here. And our classes would implement the delivery interface like this. This is the TypeScript syntax for doing this, for extending a class and for implementing an interface. The exact implementation, of course, depends on which programming language you are using. This is just some way of doing it. But now we can set the interface as a type here, and we therefore know whatever is stored in delivery will be an object which implements this interface and which therefore will have a deliver product method. And therefore now we can safely call deliver product here, and it's this if check which now ensures that we're executing this method on the correct type of object. Now, of course, you might have multiple places in your code where you need such objects, and therefore, of course, you could create a factory function again, or a factory method in some utility class, and for example, name this create delivery, where you get the purchase for which it should be created, and then you move that if code just into your factory method. You pass the purchase to these constructor functions, and then wherever you needed such a specific type of delivery, you would just call create delivery, pass your object to it, and you would then be good. Of course, we need to return the created object in the factory function. And then this factory function could be used anywhere in the code where you need this specific type of object. And now in this factory function, of course, we can get rid of the this keyword and assume that the purchase which we get here has a delivery type. Again, I just want to make it really clear. The object I do pass in doesn't have this property, but this again is just some pseudo code. Of course, instead of passing in an empty object down there where you create your instance, you would have a concrete purchase object which you would be getting from somewhere else in your application. It's just not the focus here. The focus is that we do have such a factory function which knows how to produce specific instances of our classes here based on which kind of purchase we get. And that's how you can use polymorphism and create polymorphic objects when using classes. It's basically the same idea as in the last course section, where I essentially created an object or a dictionary on the fly with the factory function. Now we're solving the same problem by using classes. So by now we learned about the difference between real objects and data containers, and we learned that polymorphism is one important aspect that we can keep in mind when we work with classes to avoid code duplication and therefore to stay dry, which ultimately is a part of writing clean, readable, and maintainable code. Now I want to have a closer look at classes in general, no matter if we use polymorphism or not. How do you write clean classes in general? Let's say you're writing some new class for whichever data entity you might have, and how should you now write this class? Well, clean classes should be small, just like functions in the end. You typically should prefer multiple smaller classes over a few large classes. And of course, that is very similar to what we learned about functions. Clean functions also should be small, they should be short, they should be focused on one thing, as you learned, to ensure that not too many lines of code are in one function and to ensure that they are always easy to comprehend and read. And it's the same here for classes now. However, there is an important difference when we define what small means exactly. With functions, we had the concept of a function doing one thing. With classes, we have a related yet different concept. Classes should have a single responsibility. And there is a principle, a well-known principle, the single responsibility principle, which actually also revolves around that. And I will come back to that principle in just a second again. The general idea simply is that a product class, for example, should be responsible for product-related issues. For example, changing the name of a product, not for changing the name of a user, for example. This might sound trivial, but it is easy to mix up these different concepts in reality. Take this dummy online shop class, for example. All the real code is missing, but you can see the API, the methods, the surface area of this class here. And you see, I got three properties here: orders, offered products, customers. Whichever data would be stored in there doesn't matter. The names give us a good idea of what is in there. And then we have a bunch of methods here for adding a product, for creating a customer, and so on. And all these methods kind of make sense, right? It's the online shop class after all, so it makes sense that we can add both a product as well as add a customer. But the problem here is not necessarily the number of methods. It could make sense to have that many methods in a class, but the focus of this class, the responsibility of this class, that's the problem, because this class doesn't just have one responsibility. Instead, this class is dealing with orders, with products, with customers, and even there it's actually having multiple purposes. It is dealing with updating and adding products and removing products, but then it also is responsible for restocking a product, which is not the same as changing a product name in the end. So this class has a bunch of responsibilities, at least 3: orders, products, and customers, but maybe even more than that. And that would be a problem here. Even if every method would just have one line of code, then this class wouldn't be big when we count lines of code, but it would be big if we consider its responsibilities. And a better way to write this code would be to split this class into multiple smaller classes, for example. And this is just one possible split here, of course. Here we could have classes which do have separate responsibilities. Again, you might even be able to split this up further But you can already see the idea here. We have multiple smaller classes where small really means that we have less responsibilities in our individual classes. And this is considered clean code. Small focused classes where I know that if I want to change something on the product logic, I have to go to the product class. And I don't have to scroll through the entire large class here just to find the product specific functions I'm looking for. That's the idea behind small classes and what you should focus on when writing classes. Keep them small and define small by looking at their responsibilities. I absolutely want to highlight that small for classes, unlike for functions, does not mean do just one thing. This product class knows how to update and remove, for example, which is definitely more than one thing. But it's the same responsibility. The responsibility is to manage the product data and the product existence. That's the responsibility here. And that's a core difference to functions. And this difference, of course, makes sense, because if we would have the same definition as for functions, then every class would in the end only be allowed to have exactly one method, right? And if you create one class per method, then this is definitely not efficient, and you would end up with dozens of super tiny classes, which probably then also would have strange names, just to have one method per class. This makes no sense at all. It basically defeats the idea of using classes in the first place. So it's not about doing just one thing, it is about having one responsibility per class. Now, when we learned about functions, we also learned about these levels of abstraction, which in the end helped us decide whether a function is doing too much. It was a part of the decision process. For classes, we also have a related helper concept, you could say, which helps us decide whether a class is too big or too small, in case you're not sure whether that could be the case. And that concept is called cohesion. Now, what's cohesion about? Cohesion, in the end, just defines how well the methods of a class are using the class properties. So how much are your class methods using the properties of that class? That's what makes up cohesion. And you would have maximum cohesion inside of a class if all methods in that class each would use all class properties. So every single method in a class uses all the class properties. If that's what you would have, then you would have a highly cohesive object and you would have maximum cohesion. Now, the opposite would be no cohesion. That basically means that of all the methods in your class, no method is using any class property. So all the class properties are not managed by your methods. Instead, they probably are public and can be used from outside the class. Then in the end, you would just have a data structure, a container, with some utility methods, as it seems, since the methods are not operating on the properties of the class at all. Now, you definitely want to avoid having a class with no cohesion, unless you want to have a data container with utility methods. Otherwise, you want to avoid this. The goal, of course, is maximum cohesion, though this is not entirely true. The goal is high cohesion, because you will never be able, or rarely be able, to achieve maximum cohesion. Instead, you're going to be somewhere in between, and you want to write highly cohesive classes, where all your methods use many of your properties. You will not be able to make every method use every property all the time, but you should have a good usage of properties in your methods. For example, if you have a look at this large class from before again, I added some comment annotations next to the methods about which properties these methods probably would be using. And I think it's fair to say that add product, update product, remove product, get available items, and restock product probably all only operate on the offered products property. So they use one of the three properties you got. Create customer, login customer These two methods probably only operate on customers, just as the update customer profile method, by the way. And then we only got make purchase and add order, which use all three properties probably. The orders, offered products, and customers properties. And refund would probably use customers and orders. So we can see that only make purchase and add order are methods that would really belong into this kind of a class, because these are the methods which use all the properties. Refund at least uses two of the properties. But generally, this class doesn't have a great cohesion because almost all methods use only one of the three properties. So there is no hard rule on when to split. You can't say if 7 out of 10 methods use at least 2 of 3 properties, then that's good, otherwise you should split. That's not how it works. But it should be obvious that in this class, many methods are only using 1 or at most 2 of the available properties. The majority indeed only uses 1 property, and that's not cohesive at all. Now, as soon as you start splitting your classes into smaller classes, you should see your cohesion grow. And definitely don't end up with the one method per class solution just because this has maximum cohesion. As I mentioned on the slide, that's not the goal. But you should end up with smaller classes which have good cohesion. So where most of your methods use at least a couple of the available properties, that's the end goal in the end. Now, when working with classes and objects, there are a couple of important rules and principles out there which you might have heard in the past already. And all of these rules and principles and laws exist to help you write more maintainable code. That is the core idea. Now, of course, as I already mentioned at the beginning of this course section, there is a relation between maintainable and extensible code and clean code, which primarily focuses on readability, but therefore is also related to maintainability. There is a connection for sure. But there are some patterns and principles which are more important for clean code, which have direct impact on the readability of code, whereas there are other patterns and principles which have less of an impact there, but which instead really help you with building large-scale, extensible, maintainable applications where a lot of developers can keep a project up and running over a long time, and where it's easy to add new functionalities and so on. And that is then only loosely related to clean code. Now, of course, here I will focus on the principles and laws which have a bigger impact on the cleanness of your code. And for that, we will start with the law of Demeter. Now, what is the law of Demeter? It is related to code like this. Here in this code, which could be in some method of some class, we are accessing the customer property of the class. On that property, the last purchase property, as it seems, and on that last purchase property, which seems to be another object, we access the date property. You should avoid code like this. Drilling deeply into other objects is something which is discouraged by the law of Demeter. Now, why is it discouraged? The law of Demeter is in the end about the principle of least knowledge, which means your class shouldn't rely too much on the internals of strangers, of other objects you are interacting with in your code. In this example, customer would be a class property, so interacting with it is fine, and accessing last purchase is fine, but last purchase now is kind of a stranger. We access it indirectly through customer, and we shouldn't drill deeper into that. Now, why shouldn't we do that? Well, because whenever something changes about the internal structure of last purchase, all our code in this place where we have this line of code needs to change as well. And that then makes your code harder to extend and maintain, because simple changes can result in a lot of changes in a lot of places of your application. And this law is closely related to our concept of writing clean code. Because for one, when writing clean code, we shouldn't repeat ourselves, and we often might do that if we have statements like this. And in addition, statements like this are a bit harder to read. Analyzing such lines of code simply takes longer than short, simple statements. Of course, this isn't too difficult of a statement, but it is also just a brief example. So the law of Demeter, which we should therefore also follow to achieve clean code, in the end states that code in a method may only access the direct internals, which would be properties and methods, of the object it belongs to. So you can access any property and method of the class of which this method in which you run the code is part of. You can access any objects which are stored in properties of that object. So in this case, accessing customer is fine because it is a property of the class this code belongs to, as you can tell by the this keyword. And accessing last purchase is of course also fine because that directly is part of that customer property. You may also use any objects which you receive as method parameters. So it's not just about properties of the class, like customer, but if customer would be received as a parameter, we would also be allowed to access data in it. And of course, we also are allowed to interact with objects which are created in the method. So if we would instantiate another class, we can of course also work with the API and properties of that class. That's the idea behind the law of Demeter. And here is this example from the slide, now in a real dummy class. I'm accessing date on last purchase on customer, which is a property, and only this part here would be okay. Because with this part, I'm directly working on the property and the data in the property, which is part of this class. Date is not directly data of the customer property, it's part of some other data which is stored in the customer property. And therefore we have only indirect access to it, which is not allowed by the law of Demeter. Now here in this example, we are for example getting this date to then call the deliver purchases by date method. And the obvious question now is, how could we clean this code up? How could we change it such that we do follow the law of Demeter? Well, one first simple solution could be that we simply go to our customer class, so to our customer object and the class defining that object's structure, and we add a new method in there. Instead of this code, which for the moment I'm commenting out, so that we still have it for reference, instead of this code, it would be better if our customer class would have a get last purchase date method. This code would be allowed because we're directly accessing a method in our customer property. And now this customer object simply needs such a method, which then internally accesses last purchase date. And there, this would be okay because last purchase, of course, will be a direct property or some data stored in the customer object. So then accessing date on that direct last purchase property would also be fine inside of that customer class. So this is how we could adjust our code in the customer class and then also in the delivery job class to not violate the law of Demeter anymore. However, this is not a great solution because now we basically force our code to follow the law of Demeter, but we still have some problems and we didn't really end up with that much of a cleaner code. Yes, this code is a bit easier to read now, so that is cleaner because it's a clear instruction which requires no interpretation. But of course, we now just outsourced the problem into customer. And whilst we technically are not violating the law of Demeter anymore, you of course quickly end up with a lot of helper methods like get last purchase date here just to follow the law of Demeter on paper. The better solution for solving problems like this, and the solution which really makes this clean, which is why I want to cover this concept, is that you should tell, don't ask in your code. Don't ask for information to then use it, but instead simply tell other classes what to do if that is possible. For example, here, instead of getting that date now with this helper method just to then forward it to deliver purchase by date, the better solution would be to work on the warehouse instead of the customer class. So that here on this warehouse, we, for example, can call a deliver purchase method instead of purchases by date. And here we pass this customer last purchase. And then it would be the job of the deliver purchase method to extract the data from that last purchase which it receives, which is required to deliver this purchase. Now we're not violating the law of Demeter because we're only accessing the customer property and some data which is directly stored in that. And in deliver purchase, we just get a purchase object, which we also can use there to extract any data we want, because you can work with objects and the data directly stored in them if they are received as method parameters. And this is now how you really would want to solve this. You want to tell your code what to do and not ask. And that's also why I wanted to cover this principle or this law here, because this certainly is clean code. We don't have to interpret why we want that date and what we could be doing with it. Instead, we in the end got rid of 2 lines of code, which we required before, which we had to read, and we just got 1 line of code, which is 100% clear about what it does. That's the law of Demeter and how you should follow it, and that's why it matters for writing clean code. And as a side note, and why I also wanted to include this in the course, which is of course not just about object-oriented programming and classes, the law of Demeter actually also can be applied to code that uses just functions and no classes. I mean, of course you can't apply it like this, you can't apply the official law with all its definitions, but you can apply its logic. If you write code with just functions without any classes because you are writing code in a procedural way or because you use functional programming. If you do either of these 2 things, then you still want to ensure that inside of your functions you don't dig too deeply into received data unless that is kind of a data container only. And you also want to tell, not ask, at least if it makes sense. You should always ask yourself whether getting some data to then do something with it in the next step is the best possible way right now, or if you maybe just instead should tell some other part of your application what to do next. This is always something you can consider because telling instead of asking is always super easy to understand and automatically leads to shorter code, at least in the part where you are telling. So the law of Demeter is super important, especially when working with classes and objects, but also if you think about the general idea behind it in other kinds of code. So now that we learned about the law of Demeter, we should dive into a couple of other often cited principles which you should be aware of when working with classes and especially when writing code in an object-oriented way. And here, amongst the most popular principles, we would have the so-called solid principles. We should write classes in a solid way. And SOLID is an acronym which stands for 5 different principles which you should apply to your classes, so which you should respect when writing code, to end up with classes which are considered to be well written, extensible, and maintainable. Now here's what these different characters stand for. The S principle is the single responsibility principle. And we're going to have a closer look at these principles over the next minutes, of course. O stands for open-closed principle, L for Liskov substitution principle, I for interface segregation principle, and D for dependency inversion principle. These are the solid principles which you typically should follow when writing object-oriented code. Now, it's especially the S and O principles which also matter to us when writing clean code, because as mentioned multiple times, whilst all patterns and principles of course tend to make our code cleaner, we especially have two principles here which have a very clear impact on the cleanness of our code. So therefore, let's take a closer look at the single responsibility and the open-closed principle, but of course let's also briefly look at the other principles over the next minutes. Now, the single responsibility principle in the end says that classes should have a single responsibility, and that's of course something we heard about before already, and that a class shouldn't change for more than one reason therefore. Now, as I said, we heard about that idea of having a single responsibility in a class earlier in this module already when I explained that classes should be small. And indeed, classes should have a single responsibility. Now, I want to highlight though that the single responsibility principle in the end focuses on changes made to a class. But of course, that simply means that if a class would have multiple responsibilities, there would be multiple reasons for code edits to be made to this class, simply because it has, well, too many responsibilities. And therefore, less responsibilities, to be precise, a single responsibility, means that code changes have less impact on the class, and ultimately, of course, that then also implies that the class is really focused and small, which was our overall goal. Nonetheless, the question of course now is, what exactly is a single responsibility? Earlier in the course, or earlier in this module to be precise, I showed you this big class with a broad API with a lot of methods. And I argued that this class would have multiple responsibilities, that it would be doing too much. And I would still say that this is true. Still, the single responsibility, as defined by the single responsibility principle, is not talking about whether a class might be doing work on both a product and a customer. Instead, single responsibility, in the context of this principle, is actually meant to refer to different, you could say, business areas this code might be related to. And to give you a better example, consider this report document class, which actually violates the single responsibility principle, even though it's super small. This class here has a method called generate report and a second method called create PDF. Now, it's violating the single responsibility principle because it's very likely that generating a report, which is about pulling data, connecting data, and so on, which is about generating the final report data that should be included in the report, that this kind of task actually is a totally different feature, a totally different area in our business organization than creating a PDF. When we talk about creating a PDF, it's about things like layout, it's about things like how many pages, and all this presentational logic. Generate report is way more technical. It's about pulling in data and connecting the right data. So it's hopefully clear that these are two totally different responsibilities. Generating and connecting and analyzing data is a different responsibility than presenting data. And that's what a single responsibility means in the context of the single responsibility principle. For example, this user class would probably not violate the single responsibility principle. It has a couple of methods which do quite different things, but all these methods are related to managing the authentication and the status of this user, be it the user creation as part of the signup method, or be it the creation of a session when the user logs in, or be it changing the authentication status and the permissions when we assign a role. We could argue that all of that is related to user authentication, and that probably is one general responsibility. Now, of course, I'm saying probably, and you could argue, because as always, this is up for discussion and it depends on your exact use case, your exact application, on what exactly a responsibility is and what not. You also might not always be able to draw a sharp border, but you should be aware of the general idea of having only one core responsibility per class, and you should also be aware that one responsibility doesn't mean just one method, as explained earlier. So what I explained earlier about keeping classes small and not doing too many things, having too many responsibilities in a class still applies. I just also want to clarify that this does not mean that you have to split a user into an authenticated user and an unauthenticated user, but that instead, for example, everything related to authentication might be one responsibility and therefore might fit into one user class. So I basically again want to emphasize that you should definitely keep your classes small and focused, but just as mentioned earlier, that you should not end up with super small classes which only have one method each. Now, I did mention that especially the single responsibility principle and the open-closed principle help us with writing clean code. Now, in the context of the single responsibility principle, which we just had a look at, why would that be the case? Well, basically for the same reason as before. The single responsibility principle, as mentioned before already, is about keeping classes small. So restricting classes to one core responsibility automatically leads to smaller classes, even if we keep in mind that responsibility does not mean task, but instead is about a group of tasks which are connected to the same feature or business area. Still, you will end up with more classes if you respect the single responsibility principle, and of course, therefore, smaller classes, if you don't overdo it, if you don't split your classes too much, lead to code which is easier to read because you don't have these long classes with a bunch of code in there where you don't know what these classes are doing and where you have to scroll a lot, but instead you end up with smaller classes which typically make managing your code and reading your code easier. Now, besides the single responsibility principle, there is one other core principle you should be aware of when working with classes, especially in the context of clean code. And that's the open-closed principle. The open-closed principle says that a class should be open for extension, but closed for modification. Now, what does this mean? Here is an example. Now again, it's just a dummy class without actual code, because again, it is more about the general architecture of your classes, the API of your classes. And what we can see is that we have a printer class, which actually has different methods for printing PDF documents, web documents, so probably HTML pages, and also print page, which maybe prints real pages in the real world. We also have a verify data method, which probably is called internally to verify the data from any of these print methods here. Now, what's the problem with this class? It basically needs to grow whenever we add new functionality. If we also want to print Word documents or Microsoft Excel spreadsheets, we need to add a new method. Whenever we need to call a new method besides verify data from our print methods, we have to add that logic to all the print methods. So this printer class might have one responsibility. It's about printing data and about generating output. But it actually is not closed for modification. We need to go back to it all the time whenever we add new functionality. It's not very extensible. And therefore it violates the open-closed principle because it should be closed for modification, which this one isn't. Now this might remind you of this polymorphism example from before, where we had these different delivery classes for delivering goods, and where we had duplicate code before we utilized polymorphism. Indeed, the open-closed principle is kind of related to that. Instead of having this printer class here, it would be preferable to have code like this. To have, for example, a printer interface, and then a base class, which just has this verified data method, which probably is shared amongst all classes. But then all these specific subclasses implement this printer interface, which forces them to have a print method, and they extend the base class to then all have a print method, which then just does different things depending on which class it is. The advantage is that the base class, the printer implementation, can be closed for modification at some point. Once the API is finished, we close it. Of course, we can still edit it if we need to fix bugs, but we don't need to edit it all the time just to add new features. Instead, to add new features, we extend it. And that, of course, is what the open-closed principle says. A class should be open for extension. And we can build brand new printer subclasses, like for example a Word or an Excel printer, which just extends the printer implementation class and implements the printer class, which then just forces us to add a specific print method again. This is how we can follow the open-closed principle. Now, why does the open-closed principle help us with clean code? Or why does it help us with clean code more than maybe some other principles? Because this extensibility ensures small classes automatically, because otherwise, if we don't extend, if we stick to the big do-it-all class instead, then this class, this printer class, keeps on growing and growing the more ways of printing we add. On the other hand, if we have multiple smaller classes, we can add more and more features without getting growing and growing classes. So it helps us with smaller, focused classes, and it can help prevent code duplication. It can help us stay dry. Don't repeat yourself. The open-closed principle helps us with that as well, because just as shown in the polymorphism example, we have all these classes and we avoid extra code duplication. And of course, both aspects, small classes and dry code, are what clean code also is about. Because that helps us with readability and of course also maintainability. But especially the readability and the understandability of the code is what helps us as humans if we analyze code. Instead of diving into this large class and looking for the right method we need, we can just jump to the specific printer class we need, and it's crystal clear what it does, and all the code in there is crystal clear. Of course, if we then also follow all the other rules for the actual code which is written in there, like for naming and for our methods. But that is why the open-closed principle matters here. Besides the single responsibility principle and the open-closed principle, which are the two most important principles for us here when it comes to writing clean code, we also have three other principles. And I want to next dive into the Liskov substitution principle, because even though these remaining three principles are not as important for writing clean code as the first two, I still want to cover this entire list. So what's the Liskov substitution principle all about then? The Liskov substitution principle basically says that objects should be replaceable with instances of their subclasses without altering their behavior. Now, this is a very abstract sentence. What exactly does it mean? Here I again got an example. We have a class bird, let's say. Of course, this is a very simple example here, but we got a class bird which has a fly method. We then got a class eagle, which extends the bird class and adds a dive method, because not all birds really can dive, Eagles, though, certainly can dive down onto their prey. And then here we got some code where I instantiate bird, not eagle, but bird, and call fly. And the Liskov substitution principle now basically says that I should be able to substitute bird down there with a subclass of this bird superclass. So here we should be able to instantiate an eagle instead and call fly on an eagle, and we should essentially have the same behavior as before. So of course, in a real program, the eagle class then might be doing more things than just the bird class. I mean, even here we can see that we can call dive in addition to fly, but we still can call fly as before on the bird, and we can still expect that fly does the same thing. So in this example, the bird flies. In a real application, we could have different databases, and no matter if it's a SQL or MongoDB database, we should have a connect method which always has the same behavior of connecting to that database. So it seems like everything is fine here, right? Well, what happens if we add a penguin class, which also extends bird? A penguin is a bird. The problem just is that a penguin can't fly. So we have the wrong base class here, the wrong superclass. Bird is a good superclass if we only work with eagles and other birds who can fly. But as soon as we start adding birds who can't fly, we have a problem. And if I have a look at this other example I briefly mentioned, where we maybe have multiple databases which all have a connect method, even there, as soon as we add a database which doesn't need to connect, let's say some in-memory database, we also have the problem of modeling our data and our entities in the wrong way. Because that's what the Liskov substitution principle ultimately is all about. It wants to ensure that you don't model your data in the wrong way. For example, here we picked a bird as a base class for all our specialized birds, and as it turns out, at the example of the penguin, that was the wrong choice. So how would you write proper code here? Well, for example, you could add another base class, let's say a flying bird, which actually has this fly method, and it's the flying bird which acts as a base class for the eagle, and it's the regular bird, which might have other shared functionalities, it doesn't here, but it could have, which you use as a base class for the penguin. And now indeed here, you can use flying bird and call fly, or use an eagle and still call fly, but you can't use a penguin. And you also don't need to substitute your flying bird or eagle with a penguin, because penguin extends bird, not flying bird. The base class, the superclass, is a different one. So that's what the Liskov substitution principle is all about. If a class inherits from another class, then you need to be able to replace that other superclass with instances of the inheriting class, without changing any behavior. And at the example of a penguin, that didn't work. Unless we added a new superclass for eagle and all other birds who can fly, because now we can substitute these classes with each other, and we can substitute bird with penguin, because fly is not built into penguin. So the Liskov substitution principle ultimately is about forcing you to model your data correctly. Now, why is it not a super important principle when it comes to writing clean code? Well, it certainly is important when it comes to modeling data correctly, which of course is an important part of writing good and extensible code. But from a readability and clean code perspective, I think it's fair to say that throughout this example here and me adding this flying bird class, the readability didn't really change. It always was very readable and understandable, and therefore the Liskov substitution principle doesn't add too much when it comes to just code readability and clean code being written. Let's continue with these important principles, though, as mentioned before, we already covered the two most important ones when it comes to writing clean code. Nonetheless, let's next have a look at the interface segregation principle. What is this principle about? The interface segregation principle says that many client-specific interfaces are better than one general purpose interface. Now again, as always, what does this mean? I got another example for you. I got a class SQL database which implements an interface called database. Interfaces are a common thing in object-oriented programming, of course. Interfaces are contracts which force classes to implement certain behaviors. In this case, we are forced to add a connect and store data method if we implement this interface. And the SQL database does implement this interface. Now everything looks all right here. But now let's say we don't just have the SQL database, but instead we also have this in-memory database, which of course also is a database, and therefore it also makes sense that we implemented the database interface. Hence, we are forced to add a connect and store data method. And now the problem is that it might make sense to have a store data method, because no matter if we are storing data in a SQL database or in memory, we want to be able to store data at the end of the day. But connect, that does not necessarily make sense here. An in-memory database, which uses the local memory for storing data, doesn't really need to connect anywhere. So in the end, we have the wrong interface here. And if that kind of reminds you of the Liskov substitution principle we had a look at in the last lecture, that would actually not be a surprise. Because here we had the problem with modeling our data incorrectly and using the wrong base class in the end. Now with the interface segregation principle, we have the problem of having a wrong interface which we force onto multiple classes, even if these classes are not using inheritance at all. The problem is that our database interface is a general purpose interface here. It tries to cover too many use cases, connecting and storing data, to be precise. And we should avoid general purpose interfaces when following the interface segregation principle. Instead, we should have multiple smaller client-specific interfaces. For example, here, we could have a database interface if we want to keep that name, but in addition, we could have an interface which is called remote database. And the connect method, forcing classes to have a connect method, would go into remote database. Then the SQL database class could implement database and remote database, which in TypeScript is done like this, simply by separating interfaces by a comma. And the in-memory database only implements the database interface and not the remote database interface. Hence, we can delete connect here. We're not forced to implement it anymore, and hence we now have code which does follow the interface segregation principle. Now, just as with the Liskov substitution principle, obviously the interface segregation principle is an important principle when it comes to writing maintainable and extensible code, when it comes to writing clean code, where it of course matters that humans can read the code quite well and that it's easy to understand. This rule doesn't help us too much. It also doesn't hurt, and it certainly helps a bit, but it's not super important. Now let's conclude the solid principles by having a look at the last principle in this list here. The dependency inversion principle. What is this principle about? The dependency inversion principle says that you should depend upon abstractions, not concretions. And that's a super fancy term which, I don't know about you, but which might be totally unclear. At least this sentence was totally unclear to me when I first read it. It is, however, not even close as complex and complicated as it sounds. And if you are following the other principles already, then chances are pretty high that you're already following this one as well, or at least that it's very easy to follow this one as well. Now here I got another example which actually is very close to the interface segregation principle we covered in the last lecture. Following the interface segregation principle, I got two interfaces here, a database and remote database interface. And then I got two classes, the SQL database class and the in-memory database class, which actually use these interfaces. Now, I also got an app class down there where I actually need a database as an argument in the constructor. And that database either has to be a SQL database or an in-memory database. This app works with both. But depending on what it is, I have to run the connect method as part of my constructor. That's why I have this if check here. The problem with this example is that we depend on concretions. I depend on the concrete implementation of my database. I accept both types here, and therefore I have to check which type I'm getting so that I can execute this extra code which I might need to execute. Now, it should be needless to say that code like this can be hard to maintain, because the more types of databases we add, the more if checks we might need to add here. And whenever the connect method changes, we also need to change it in all the places where we do have a check like this and where we do call connect. So therefore, this could become a problem in bigger applications where you maybe also have different kinds of databases. Now, we can change the code to follow the dependency inversion principle though. And changing it will be very simple because I'm already following the interface segregation principle here by having my different interfaces. These interfaces in the end are abstractions. I can use these interfaces to buy certain functionalities, to ensure certain functionalities without knowing how exactly they work under the hood. But I can rely on the fact that, for example, a connect method or a store data method is there. And then here in this app, we could say that in the end, all we want is a database. I don't want to deal with connecting here. I just want to ensure that the type of database I have here, the type of this argument, is of type database. So it should be a class which implements the database interface. And the database interface in the end just ensures that there is a store data method, not that there is a connect method. So therefore, of course, we should remove this if check because we know we get a database which only has a store data method and we don't have a connect method here. Instead, it's now the place where we create our app where we have to provide a database as expected by this class. And that's why it's called the dependency inversion principle. We no longer care about the data here in the app class, so in the consuming class. We don't want to check which kind of data we got here. Instead, we invert the dependency. And we don't depend on the type of database, but instead, we force whoever is instantiating that class to provide us a database which fulfills this contract. And just this contract. So wherever we are instantiating the app class, we now need to pass in a new database. And therefore it's now here in this place where I, for example, need to create a new SQL database and also call connect here. Because that's now my responsibility here in this place. The app doesn't care about it because it inverted the dependencies. It tells me to provide a proper value. It doesn't want to check it internally. And this tends to be more maintainable because you can even use dependency injection frameworks and approaches to have only a few places in your application where things are created. So where, for example, this database is created and connected. And to have many places in your app where you then depend on this abstract database. That's the idea of the dependency inversion principle, and that's how you write code that follows this principle. Now, of course, like all these principles, there also is a connection to clean code here. By inverting the dependency, of course, we reduce the amount of code we have in here, and that of course automatically makes this smaller, more readable, and avoids code duplication. So it certainly matters. But the dependency inversion principle is also kind of a result, or at least strongly related to the other principles. And in addition, the key benefit definitely is maintainability and extensibility. So of course it matters, all these principles matter, but I would argue it's not as important as the first two principles which were covered, the single responsibility and the open-closed principle. Nonetheless, we now had a look at all these solid principles which are popular for a good reason. And if you are working with classes, and especially if you are following a project-oriented approach, if you are writing code in an object-oriented way, you should also consider and respect these principles, because ultimately they will lead to more maintainable and extensible code, and as a great side effect, they also tend to give you cleaner code.